So a warm welcome to this part one of the webinar series about async await. Today we talk about async await best practices. So I'm Daniel Marbach. I'm a solution architect. I call myself an enthusiastic software engineer. I'm a Microsoft MVP for systems integration. I live in Switzerland. Currently it's snowing and quite cold in Switzerland. But if you want to know more about me, I recommend you to listen to episode 77 of the Developer on Fire podcast. You can reach me on Twitter under @DanielMarbach and a blog under the particular blog particular.net/blog and on planetgeek.ch, which is my personal blog. I hope you guys subscribe after this webinar. So in this webinar, we learn important terminologies around async await. We learn the difference between CPU bound and IO bound. We learn the difference between threads and tasks, and we'll learn a few async best practices. This webinar is divided into three parts. The first part is the terminologies. The second part, we talk a bit more about code. We dive into the code, and at the end, we have a wrap-up with a Q&A session. Don't hesitate to put in your questions during the webinar into the question field in the GoToWebinar settings, and we will be collecting them and answering them at the end of the webinar in the Q&A wrap-up session. So let's first talk about important terminologies around async await. The first one is, of course, async. So async in the real world can be compared to me doing the laundry. I put my dirty clothes into the machine and select the program or timer and let the machine do its work. Until the laundry is done, indicated by a beep of the machine, I can carry on with other things like reading the newspaper, playing with my son, or whatever I feel like doing. So I, as the worker, I'm free until the external task resource, like here the washing machine, is done and has indicated that back to me. This is very similar to software. A software or an asynchronous program dispatches the tasks to devices that can take care of themselves. So that leaves the program free to do something else until it receives a signal that the results are finished. Asynchronous programming should be used for external operations which support event-driven callbacks, so when they are done. Usually this is the case for IO-bound work. For example, on Windows, you have a thing called IO completion ports. IO completion ports indicate when an IO operation is done successfully or not successfully back to the initiator of the asynchronous IO operation. Async operations can be more efficient since the worker initiating the work are not blocked. Let's talk about tasks. I'm talking about the system threading task class. System threading task is an abstraction layer which represents both CPU-bound and IO-bound operations as a uniformed API. I define a task as it represents the state and the outcome of an asynchronous operation executed now, later, or never. This is very similar to washing my clothes. If a task represents an IO-bound operation, then we could compare it to the laundry machine. So the state of the task, or here the laundry machine, is running, not running, or completed. The outcome of the task, hopefully, is clean clothes. I can late start the machine with a timer, or the machine can decide to run a health check before the process starts. It's also possible that because of failures, the machine will never start and I will not notice it until I come back. Or even more likely, my wife cancels the process because yet again I've chosen the wrong temperature. That has never happened to you. Hopefully. So let's talk about CPU-bound tasks. CPU-bound task can be compared to me doing the laundry manually. While I'm doing the laundry manually, scrubbing my clothes with some soap, I'm completely blocked. I cannot read the newspaper or do something else in the meantime. No matter whether the task is I/O bound or CPU bound, threads are the workers responsible for getting tasks done that are currently scheduled on the current task scheduler. But with CPU-bound tasks, the worker thread is completely blocked. So that means a thread can only handle one CPU-bound task at a time. In contrast, a thread can handle multiple I/O-bound tasks concurrently. Concurrent. What does concurrent mean? Concurrent is like me while doing the laundry, walking into the kitchen, I put my newspaper away, fill the remaining dishes into the dishwasher and start the dishwasher and go back reading the newspaper. So I'm doing all that concurrently. In software, this means there is a coordinator called scheduler which deals usually on a single thread with multiple concurrent work items. These work items can be interleaved, but they don't have to. Depending on the scheduler, work can also be distributed over threads and processor, but it doesn't have to. Parallel, on the other hand, can be compared to the laundromat. Multiple people can simultaneously wash and dry their clothes in the laundromat in parallel. In software, this means a parallel program is divided into independent sub-expressions that are evaluated simultaneously on different processors or threads. The goal of parallel computation is to finish the computation much faster. Parallel computation is ideally suited for CPU-bound work, such as sorting data in memory, filtering data, and so on. To be able to benefit from parallelism, the problem itself has to be able to be divided into individual sub-items which can be worked on independently. You can achieve parallelism by using concurrency constructs, but not the other way around. So let's talk about continuations. When the laundry is done, I can take out my clothes out of the laundry machine and dry them in the dryer. So the drying process is a continuation of the laundry. In an asynchronous programming model, a continuation is, or at least to my definition, a function that is scheduled for execution after its prerequisite function has completed. So let's dive into the code. Because we already have set the baseline with all these terminologies. So async await are keywords. They are here to reduce the nesting of continuations. I call them also Christmas trees, or I call nesting programming Christmas tree programming. So async await as keywords, they drastically simplify your code. So in essence we can say async await is basically syntactic sugar augmented with compiler magic. So let's see. In our laundry example, this means instead of writing clean laundry dot continue with dry laundry, we could write just this: await clean laundry, dry laundry. That's all there is to know, but let's see how this essentially reflects itself in code. So we have here a test called CPU bound, and we have here everything you can use to do CPU bound operations. So we have here parallel for, which allows me to execute the CPU bound method 1,000 times on multiple threads. Parallel for each is basically similar to parallel for, but it operates directly on an enumerable. As we can see here, we have task.run with a CPU bound method. We should only use task.run with CPU bound operations, not with I/O operations, which we will see later. The same applies for task.factory.startNew. It should only be used for CPU bound methods. So as you can see, because we have a uniform API, the await keyword can be used to await these CPU bound tasks as well. I'm not going to execute this code because this would take too long. So let's go to IO-bound work. We have here an IO-bound operation, which is called IO-bound method. So this IO-bound method creates a file stream, creates a stream writer, and writes something asynchronously into that stream writer, which represents the file stream. What happens is the unit testing thread here entering this await method, everything here, so the using statement here, the using statement here, will be executed synchronously on the thread entering this method, so therefore the unit testing thread. As soon as we come here to the first await keyword, you can see it like each await statement in your code is an opportunity for the entering thread to go back and do something else async, like me reading the newspaper during the laundry process. So that means in theory the unit testing thread could exit here, do something else, and as soon as the IO completion port indicates that this operation writeLine async is done, it comes back, the writer is closed, the stream is closed, and the writer and the stream are disposed. So let's execute this. Of course, there's nothing surprising here. So let's see what the task-based API allows you to do even more. We create here an enumerable of 4 task delays, which will wait 1.5 seconds. And then we await the outcome of these tasks sequentially. So what does this mean? So this means this test is going to last for approximately 6 seconds. Okay, let's zoom in. As you can see, sequential took approximately 6 seconds to execute. But since the task API is much more composable, what we can also do is we can execute this task concurrently if our program logic allows us to do this. So let's see, enumerable.range, we select, we do task delay, again, of 1500 milliseconds, and then instead of doing a for each await task like above here, we just do await task when all concurrent. So this starts all these tasks concurrently, and then we await the result of all these concurrent tasks with a single call. And as we can see, this now takes only 1.5 seconds. So allow me to go to the next example. Let's talk about async void. An async void operation is the following method. We have a void method which is marked as async. This void method does nothing else than just console writeLine, task delay, console writeLine, and then it throws an invalid operation exception. We have a surrounding code here, try catch, which catches the invalid operation exception. So let's see what happens with this code when we execute it. We execute this test, as we can see, going inside async void, going to throw. But the test didn't fail, and we don't see the console writeLine here. That's strange. So let us dive into what async void actually means. So async void was introduced for event handlers primarily, because these are event handlers like in Windows Forms or WPF applications. These are top level events, and if you want to write an await statement in a top level event handler, the only thing you can do is mark it as async void. When in event handlers exceptions are raised, these exceptions are raised in the background on the current synchronization context. The same behaves here when I have an async void here in my async void method here in my test. As you can also see, from IntelliSense, this method is marked as void. So I have no indication as a caller of this method that this method, I cannot do try catch around it. So the exception we just raised here, it's raised behind the scenes in the background, and there is no way, or almost no way, I can intercept the exception. In fact, there is a way. I would need to write my own synchronization context, but this is out of scope for this webinar. So the only thing, or the best thing I can do is I switch over, return a task, I await the method here, and then I execute this test again, and now we can see the exception was raised, it was catched by the test, try catch, and we have the console write line, which represents the invalid operation exception with the gotcha message inside. So what happens underneath is that if we return a task instead of async void, the compiler-generated code will make sure that any exceptions raised in the asynchronous method will be captured with an exception dispatch info and will be added to the task's internal exception dispatch info list. And on each and every await statement in my call stack, the compiler-generated code will rethrow the exception to the caller. So never ever use async void, only if you have to, so like in event handlers. But if you're writing your own code, your own library, you should really avoid async void. You should always return a task because it allows you to better compose those methods together, and you will not be running into surprising error conditions like we've just seen here in this code. So now let's talk about ConfigureAwait and configuring the context. I have to start here an application, a Windows Forms application, to explain it a little bit better. So I'll attach the debugger to the external process, and we step into this Windows Forms application. So this Windows Forms application here has several await statements. And what I'm doing here is I'm visualizing the synchronization context. So as you can see here, when I enter this application, the synchronization context, the current, is set. When we step over this code, so synchronization context is not null. Now we step into the first async method. We step into the first async method. As we can see, the first line is still executed on the same thread entering that method, so the synchronization context is not null. Now comes the first await statement. When we write after await ConfigureAwait false, what that means is the underlying state machine will not do context capturing. So it will not capture the currently executed synchronization context, so this one here, will not be captured, and it will not be restored when the continuation, which is this method here, will be executed. So let's see that. So as we can see, I did F10, and now I'm in the continuation of this previous line, and here now the current synchronization context is null. The problem is of this ConfigureAwait false is that I have to write ConfigureAwait false for each and every await statement I want to disable context capturing. By default, ConfigureAwait true will always be there. So if I don't write ConfigureAwait false, the default will be ConfigureAwait true. And as we can see, if I debug, step out of this method, now here, because we didn't have a ConfigureAwait false, the context is restored and the current context is no longer null, it's the same context again. And when we step into the same method and write here on the top level, ConfigureAwait false, we dive into here. Remember this line is still executed synchronously on the calling thread. We go into the first await, we disable context capturing, we go into the next await. Here I don't have a ConfigureAwait false, but here as we can see the continuation of this method is this method. So here the synchronization context is null. So what does that mean for us? Every time we write ConfigureAwait false, this means the thread executed can essentially be scheduled on the thread pool and the synchronization context doesn't need to be captured. In a UI application, this means every time I use ConfigureAwait false, the user interface thread will not be hammered with tasks when the continuation comes back. So essentially, depending on the stuff I'm doing, ConfigureAwait false can optimize also my Windows Forms applications. So, but this becomes even more important for if you're writing a library. If you're writing a library and you don't know where your library will be used, you never know. It's important that each and every await statement in your library uses ConfigureAwait false so that on the top level, the one who is using your library has the ability to decide whether they want to do context capturing or not. And if you context capture internally and you're doing it wrong, like I'm showing you in the next example, you risk getting a deadlock. This brings us to the next async await best practice, which is don't mix blocking and async code. So I set here the synchronization context to simulate a WPF application. I have here asynchronous method, which is using await task.delay milliseconds. And someone said, yeah, you know what, I want to write a synchronous wrapper, which is internally using the asynchronous version, because here I've already written the logic. Why not just reuse it and do a blocking wait or a .result call? Now that's a simple implementation, isn't it? But let's see what happens. So if we execute this method here, this test, let's execute this test. As we can see, this test will be running for the remainder of the webinar and will never complete. So what can we do to mitigate that? First of all, don't write synchronous wrapper over asynchronous code. It is as simple as it sounds. So what it means, if you're writing asynchronous code, everything in your call stack should be async, should be returning a task, and depending whether you have an await statement or not, should be marked as async. That's it. We could mitigate it here by applying the best practices I told you before by doing here ConfigureAwait false. If we do that, the context will not be captured and the test will execute and finish in no time. But still, instead of risking to run into deadlock code, it's better that you just write async code everywhere if you need async and if you need to benefit from IO-bound operations. So, let's go back to the slides. That's all I wanted to show today when it comes to async best practices. So let's go to the wrap-up. As we've just seen, I was just using the task-based APIs. So what that means for you, stop thinking in threads. For the most applications, threads are no longer relevant. Think in tasks, and rest assured that the task parallel runtime library is heavily optimized for most production scenarios. You don't need to worry about that. What does this mean for NServiceBus or for the next yet to be released NServiceBus version V6? We applied the async all the way up and down best practice as well in the NServiceBus V6 codebase. We also applied the other best practices like the ConfigureAwait false consequently throughout the codebase of NServiceBus V6. And we also have a roles analyzer written by us, which checks that everywhere we have an await statement, we essentially write this ConfigureAwait false. I will be linking the Roslyn analyzer in the show notes so that you can have a look at this analyzer and maybe also use it in your project. So let's do a brief recap. Use task.run or task.factory to start new for CPU-bound work. Use tasks directly for I/O-bound work, and use async task instead of async void in your code. Libraries and frameworks should be using ConfigureAwait false for each and every await statement. And please try to make sure that you're all the way async all the way and you don't mix blocking the asynchronous code, because the consequences could be, depending how it is used, that the code is going to deadlock. So in the next webinar, we will dive deeper and write a message pump for the service bus, which combines async await with the task parallel library. We will learn the task parallel library contains some unpleasant surprises and how we can work around those. So please join again and maybe invite your friends and learn to apply more than just the basics of async await. And by the way, since you're here, you have already signed up. You don't need to sign up again for the webinar. But if your friends sign up for the webinar after this webinar, they also get the recording sent to them by email so they can catch up for the next webinar. The next webinar will be using the things we've just seen today as a foundation level and will be assumed in the next webinars. All the slides I've just shown here, all the links and also the code you've just seen here is available on my GitHub account under the following address. We will also send you this address in an email after the webinar. So let's dive into some questions.
Unmuted.
So, Daniel, hello everyone. We have an interesting question from Miguel that is asking, when should I use the async and await keywords and pattern instead of the NServiceBus publisher subscribe pattern?
Okay. I'm going to answer this question, this particular question, in the third webinar, where I show how NServiceBus V6 can be combined in a message handler with the new async API and leverage the async await keywords to, for example, if you're doing, I give a brief explanation, if you're doing multiple web service calls or multiple I/O resource calls in the same handler, you can essentially do those concurrently. But I'm going to show an example in the third webinar.
There's another question from Albert that is asking if in the next webinars, are you going to speak more about execution context and synchronization contexts?
I haven't planned to talk about synchronization context and execution context because I think it's way too deep for this three-part webinar series. But if people like to dive me into those, let's say, implementation details, synchronization context and execution context, I can definitely do this. So please provide some feedback. Please hammer Brit King, and I will do a fourth or even a fifth webinar if people like it.
Thanks. There's another question from Madhav, hope I pronounced the name correctly, that was asking which tools are you using while debugging and testing the demo that you showed?
I always get this question. So I was using the Oscode debugger extension.
There's another question from Patrick that is asking, how does NServiceBus benefits from async await given that messages must honor queue semantics, first in, first out, if a queue is configured for maximum thread, how does releasing the thread to IOCP help?
Okay, so NServiceBus, as it is a messaging framework and ties into a transport like Azure Service Bus, RabbitMQ, and other transports, it's a heavily IO-bound domain. So what that means is, previously we have been using multiple threads to consume the messages. Now with V6, we can essentially, because everything is IO-bound and everything is using a task-based API, the thread consuming or picking up the messages from the queue is free to pick up other messages. Of course, you can control that by setting the max concurrency. So we allow you to say, okay, I only want to handle one message at a time, or I want to handle multiple messages at a time. But that means the new version can use the resources much more efficiently on the boxes NServiceBus is running. And this becomes even more important for things like the cloud. I will be diving more into this in the third webinar and explain it in more details.
Thanks. I think that there's two questions that can be related one to each other. One is from Jack that is asking, could you give a brief recap on what synchronization context actually is? And the other one is from Brett asking, I'm trying to run a WPF application without the UI, and I've noticed that the async await functionality is significantly different. Would you have an explanation about that?
Okay. So I usually try to explain the synchronization context. It's like a message pump or an inbox, a single-threaded one. So every operation which has to be joined back to the user interface thread is essentially guarded by the synchronization context. You have one synchronization context usually per Windows Forms or WPF application. Of course, if you have things like splash screens, you end up having multiple synchronization contexts. But let's assume we have one. So what happens is the asynchronous operation is enqueued on the synchronization context, and behind the scenes, a thread is one by one getting each of these enqueued operations and execute them, and therefore the access to the user interface elements is guarded, is single-threaded. Does that answer the question? But that being said, I mean, if people like me to dive more into synchronization context and execution context, I can definitely do that in a fourth webinar, in a deep dive.
Thanks. There's another question from Patrick that is asking, if you have a deep call stack where you are doing async await all the way, but none of the methods need to observe the task result, awaiting, is it better to return the task without awaiting until the end, or mark all the methods async and await each method call?
It's better to return. I can briefly show you an example and the influence of this. So let's say we have code like this with two methods. So let's see these two methods. So the one is doing an await, and the other one is just returning the task. So if you have a single operation, a single asynchronous operations in a method in the call stack, and you're not using things like try, catch, or using blocks, that's important, then it's better to just return the task, because what happens is you're essentially shortcutting, by not marking it as async, you're shortcutting the state machine generation behind the scenes. So let me briefly show you what happens behind the scenes. I have it here decompiled. So what would happen in the first example does not shortcut. This is the code which gets generated. So it creates internal classes which capture the state, and the state is restored. But if you just return the task, as you can see, the generated code behind the scenes doesn't have the state machine bloat like here. So it's more efficient. It's also more memory efficient if you just return the task. If you only have one asynchronous operation. If you have multiple asynchronous operations, usually for the majority of the applications, it's simpler to just mark it as async and do an await. But the other benefit is, since we don't await, there is no context capturing. So here in this example, the context will not be captured. The context will only be captured when we have an await statement. I hope that answers the question.
There's a follow-up from Brett that was asking about the WPF application without a UI, but I think that it's much easier to handle it offline instead of diving into that specific issue. The last question that I have is, well, I lost it, sorry. If we have a V5 handler that needs to use async libraries, like async EF queries, what's the best way to avoid deadlocks? And will this allow an NServiceBus V5 handle more messages concurrently, handling new message while awaiting for an IO operation to complete?
So the short answer is no, but let me briefly show you something. So for people not familiar with NServiceBus, so when you handle a message, you essentially write a class, public class, myHandler, and you implement an interface, iHandleMessages, and here is the message you want to handle. That's the basic principle. What that means is you have to implement a method which is called public void handle, and you get here the message instance message. So, but it's also, I'm going to explore that a bit more, but the worst thing what you can do is here async void, remember? I'm going to show what happens exactly if you do that in the third webinar, so never ever do that. So if you have asynchronous code in here, what I can advise you to do is, and that also prepares you for the next version, is to do something like this. Private async task handle internal my message I bus, let's call it context. You'll see why I call it context here, and then you write your async code here, and then what you do on the top level, you call handle internal, you pass in the message, you pass in the bus, and you do get awaiter, get result. So what's the difference between get awaiter, get result, and get awaiter handle internal.wait? The difference is wait will throw an aggregate exception, essentially wrapping the original exception. So if this code will throw some entity framework concurrency exception, the concurrency exception would be wrapped into an aggregate exception, and you would see in the log statements or in the error queue on the headers of the message, you would see this aggregate exception. If you write this one here, it will extract the inner exception and rethrow the inner exception, the concurrency exception. So I suggest you use this one, but you won't get more performance, more concurrency, because this is still a blocking operation. You have to wait until V6.
Thank you.
Any other questions?
The last one is from Daman, that is asking still about the synchronization context, and they're asking, for example, in Web API, how do I know whether to use ConfigureAwait false and what context do I lose after?
Okay. So I'm not an expert in Web API, so Mauro, you might be able to help me here. But as far as I remember with Web API, I think you shouldn't be using ConfigureAwait false if you want to get access to the HTTP context of current. But I think, Mauro, you can help me out here.
Yes, if I recall correctly, that's the main reason to not use ConfigureAwait false. The current HTTP context is captured by the Web API custom synchronization context. So if you need to access during the async pipeline the HTTP context, and that's maybe it's desirable, then you don't need to call ConfigureAwait false.
But if I can dive deeper into this and write a detailed answer, because I'm not an expert in Web API. Any more questions?
There's the last one that is, if I'm developing a library and want to expose an async API, is it good practice to provide the non-async methods as well? And what advice could you get how to avoid code duplication?
Okay, so the answer is, you might want not to hear this answer, but this is the truth. So my personal opinionated opinion is, and I've been wandering around in the open source community and telling people that, is if your library is in an IO-bound domain, or primarily IO-bound, all the IO-bound paths should be async only and should not be providing synchronous methods. Because, I mean, let's face it, more and more applications and systems will be using APIs which will be async enabled if they're IO-bound. So I think we will be seeing less and less usage or demand for the synchronous APIs. And it's pretty easy to write synchronous code into async code. I can show this in the next webinar. So in order to avoid code duplication, the answer is only provide the async version. Because then on the top level, users can always synchronize or synchronously call this code, like I've just shown in the previous example with the NServiceBus handler. But then it's the decision of the user to decide whether they want to call it synchronously, asynchronously, or whatever they want to do with these APIs. And you don't risk getting issues filed on your issue tracker about blocking calls or deadlocks. And that's my recommendation. Okay, we are approaching the end of the webinar. So thank you very much for listening to this webinar. And if you have more questions, feel free to ask them in the next webinar, or you can also reach me on Twitter at Daniel Marbach, or write me an email at daniel.marbach@particular.net, and hope to see you next time.